So this is all about connecting the graphs of, or the derivative and the second derivative with the original function. So the following test applies to a continuous function f of x. At some critical point c, if the derivative changes sign from positive to negative, what we're saying here is the slope is changing from positive to negative. The slope is changing from positive to negative. What did we just talk about? What kind of point is that? Is that point a maximum or a minimum? It's guaranteed to be a relative max or a local max. For sure, it might be an absolute max. We don't know. It could be an absolute max. Yeah? Is there any other way it could change from sign from positive to negative? Well, we could have a cusp. Right? And it's still a local max, and it could be an absolute max. There's just two different conditions, right? Because f prime of c equals 0. There's c. F prime of c equals 0. And this one's good. F prime of c does not exist. Okay? So f prime changes from, oh, and if we were looking at it in a table format, maybe we should do that too. So what we're going to look at here is we're going from negative infinity to some value c infinity, and it changes sign from positive to negative. So when you see that in your table, then this point has to be a local max. Or an absolute max, but guaranteed to be a local max. Yeah? Okay. Next one. So we change from negative to positive. So the obvious one's that, and then the not so obvious ones are, you know, that kind of action. Any kind of f prime of c does not exist kind of action, right? I put a corner point there, but it could have been a cusp. What else could it have been? Similar idea, yeah. So f prime of c doesn't equal 0. F prime of c does not exist. So we got critical points at c, and these ones are guaranteed to be local mins. Guaranteed to be a local min. They might be absolute mins. F prime does not change from positive to negative at C. Oh, do you want a little table over there on the side so you know what it, you get the idea? It's, right. F prime does not change sign. Does not change sign. So here it's positive the whole way, but f prime of c does not exist. It's positive the whole time. Or it can be legit. This is positive the whole time too. So those are both positive slopes. Positive does not exist. Positive, positive, 0, positive. Then do you want little graphs and negative ones, or you get... Does that guarantee anything? Does it guarantee a local max or a min? Absolute max or a min? No. Okay, if the derivative is negative... Okay, we've got to draw a picture for this one. So, if f prime is less than 0 when x is bigger than a, the slope is negative when you're going to the right of a. What are you guaranteeing? Anything? Guaranteed absolute max? Could be an absolute max. Could be an absolute max. Yeah. Doesn't guarantee it. Just says there could be. So that's f prime of x less than 0. It could be an absolute max. And then no, local maxes are only at interior points. Okay. Could be an absolute max, not a local max. Not allowed to be. They're not defined that way. Except for then the textbook says it has to be. Oh, that's stupid. They're contradicting themselves. They're allowing it to be. Okay, fine. Because we define local maxes and mins at interior points. If you flip back in your notes, I'm contradicting myself right now. It means we're contradicting ourselves right now. At a critical point C, no, let's flip back in your notes. I'm going to flip back and look and make sure. How do I define critical point? It's 4.1. Yeah. Yeah. It's a point in the interior of the domain. Oh, I guess it's alright. It's kind of a silly way. Critical points are only allowed to be the inside of the domain. And see how the book's weaseling, or how we're weaseling our way out of it? F prime of C is a critical point. C's are only allowed to be in the interior of the domain. Local maxes and mins, absolute maxes and mins, don't have to necessarily be at critical points. Because if they're at the end points, that's dirty. Oh well. I guess we were splitting hairs earlier, and now I guess we don't need to split hairs. So it could be an absolute max, and it has to be a local max. And then if f prime of, and they weasel out of it because we use the letter A instead of C. And then the other way of looking at it, here we are at A again. And here it's bigger than 0. So A has to be local min, check, absolute min, question mark. Oops, I bumped the button. What are we going to do? Woo. At a right endpoint. Is it going to look any different? No. So here we are at A. The derivative is less than 0. And the derivative is bigger than 0. So local min, check, absolute min, maybe, local max, check, absolute max, maybe. So we can get this just by looking at our table. When we see the plus minus in the table when we're doing stuff, then it's giving away what those points are. So when we build the table, because that's actually how I'm going to get you guys to do this, when you build the table, when you see it go plus, minus, you know it's a local max. If you see it go minus, plus, you know it's a local min. If you see it go minus, minus, you know just funky stuff's happening, right? If you see the curve stop, most curves will continue on to positive infinity, but if we stopped at some value b, and then you see this minus and then b, and then you're going to go, oh, it's falling into b. B's got a local min. You know what I mean? So you don't actually need to graph it. So, find the critical points, find the extreme values, identify the intervals on which the function is increasing and decreasing. Okay, so first thing we need to do is to identify the domain. Before you even start, you need to tell me the domain, because if the domain isn't all real numbers, the endpoints need to be considered. Okay? So x cubed minus 12x minus 5, what is the domain? X is all real numbers. Okay. So you can't test the endpoints because there's no way you're allowed to substitute infinity in. As much as you would like to do that, you cannot. Okay? We could use end behavior to talk about what the function's doing on the end. We could say g of x equals x cubed, and we could do a quick little sketch of what x cubed looks like. No? No. Solve analytically. Take the derivative. F prime of x equals 3x squared minus 12. How do you find critical points? Make the function equal 0. Okay, so the next thing that we need to do is we need to find the y values. So when x is positive 2, f of 2 is 8 minus 24 minus 5. Negative 21. Now we need to find out what f of negative 2 is. Negative 8 plus 24 minus 5. 11? Okay, so we've done that. Find the critical points. Check. Find the extreme values. Find the function's extreme values. Local and absolute. Okay, so we know there are no absolutes. How do we know that? Think about the graph of y equals x cubed. It looks like this. Are there any absolute maximums and minimums on that curve? No. So there's only locals. So now we have to decide, are those, which one's the local max, which one's the local min? But that's tough to do with a table. Always got to build the table. So we're going to start at negative infinity. What? Shh. We don't know. Especially if I didn't find the y values, you don't know. If I was lazy enough to not even to bother find the y values. So we're going to go from negative infinity to the first critical point, negative 2, to the next critical point, positive 2, to the next critical point, to the next critical point, to the next critical point, to the next critical point. You just keep on working your way across. Okay, so the derivative. Now, I was really kind of sloppy here because I solved it like a grade 10 student would. Yeah? They would move to 12 and, yes? One of the things you kind of want to get away from doing is this technique. While it works, It makes more work for you later on. It's actually better to think about it like this. Now, I know I'm a big fan of factoring, but it actually makes things easier. You're like, really? I don't believe you. I'll show you why it does. Okay, so we're going to pick a number. Pick a number between -2 and -infinity. -100. Okay, 3 times -100 squared minus 12. Can you do that with your brain? I can go 100 plus 2 is 102, positive. 100 minus 2, sorry, -100, -98, -102. When you multiply two negatives together, you get a positive. When you multiply by 3, it stays positive. See why it's actually easier to use the factored form? The calculation of the sign, whether it's being positive or negative, is actually easier to do. You get what I'm saying? You picking up what I'm laying down? Mr. Let's stop. Okay, we know this is 0. This is a critical point. Next one, pick a number between -2 and +2. 1. 0. Now, no matter which one, this one's easy to do. 0 squared is 0. 3 times 0 is 0. 0 minus 12 is negative. Or 0 plus 2 is positive. 0 minus 2 is negative. A positive times a positive times a negative is a negative. No matter how you do it, you get a minus. Notice I'm not writing down the number itself. All I'm interested in is the sign, S-I-G-N, of the answer. Pick a number between 2 and infinity. Square root of 23. Yeah, I know. 5. 5 times 5 is 25. Times 3 is 75. Minus 12 is positive. Or positive times 7 is a positive times a 3 is a positive. Positive times a positive times a positive is a positive. So we got increasing, decreasing, increasing. You know that's 0, and that's a critical point. So it goes increase, decrease. So it's climbing and then falling. What does -2 have to be? Max. And then it goes falling and then climbing. What does +2 have to be? A min. That's especially good if you don't take the time to find your y values, right? It's obvious if you know the y values, but it's not obvious if you don't know the y values, yes? Okay. So then we can come over to the curve, and we can plot all this lovely information. -2, comma, +11. +2, comma, -21. Yeah, about here. So we're going to make it, I want you to make it climb into -2. Climb into -2. Increase to the left of -2. Go horizontal for a split second. Fall to +2. Go horizontal for a second. And climb out to infinity. Isn't that exciting? So you put it in your calculator, it looked just like that. Yay. Okay. X squared minus 3 times e to the x. What's the domain? All real numbers. Take the derivative. Product rule. Derivative of the first times the second plus the derivative of the second times the first. plus. It's the new product rule. It's version 3.0. Decided to change it last night. Sorry, I didn't tell everybody. Do what? Make it equal to 0. So you get, now I'm going to factor a common term. What is the common term? E to the x. So you get e to the x bracket 2x plus x squared minus 3 equals 0. Now I'm about to get all math 11 on it. So e to the x equals 0, or x squared plus 2x minus 3 equals 0. Newsflash, folks. Will this ever equal 0? No. No value of x. Well, negative infinity would, but we're not allowed to say negative infinity. So, if you don't believe me, how would you solve for x? You would ln it, yeah, use logarithms. X ln e equals ln 0, and ln 0, as soon as you type it in your calculator, you get laughed at, right? So it blows up in your face. What are you going to do over here for this part? Oh, I love factoring. Well, you should marry it then, Mr. F. X minus 3 plus 3x minus 1. Yes? So we have two critical points, -3 and +1. So technically we should go get some y values. That would be exciting. You want to be excited? Y values would be -3 squared, 9. 9 minus 3, 6. It'd be 6 e to the -3 would have be that y value. And then put in +1, and you would get 1 squared is 1, minus 3 is -2. So it would be -2 e to the 1. Isn't that exciting? You want to reach for your calculator and type it in as a decimal, don't you? I could see it in your eyes. Just say no. Okay, so we got our y values. Well, everybody knows where 6 divided by e cubed is. Like, come on. No? Oh. Okay, so we're going to go from -infinity to the first critical point. -infinity to the first critical point is -3. To the next critical point, +1. To the next critical point, positive infinity. F prime of x. F of x. Now, we're going to look at the derivative like this to help ourselves out after doing all that good factoring. We should look at it as e to the x, we should look at it as x plus 3, and we should look at it as x minus 1. Okay, pick a number between -infinity and -3. -4. Okay, e to the -4, positive. -4 plus 3, negative. -4 minus 1, negative. What is a positive times a negative times a negative? Thank you. Increasing. Okay, pick a number between -3 and +1. 0. E to the 0, positive. 0 plus 3, positive. 0 minus 1, negative. A positive times a negative is a negative. Decreasing. Pick a number between 1 and infinity. 2. Positive, positive, positive. 0 CP, 0 CP. So if it goes increasing, decreasing, we know -3 is a max. And it goes decreasing, increasing, we know +1 is a min. Local max. It's a local max check. Absolute max we don't know. And we know this is a local int. Okay, so we can plot those points now. Yeah, now I guess you can reach for your calculator. Maybe. And when you throw that in your calculator, I'm going to cheat and look at it. Oh yeah, right, it does this. So negative 3, 6 divided by e cubed is really close to 1. It's actually a little smaller than 1. And then negative 2 e to the 1, that's like negative 4, negative 5-ish. Looks like this. You'd have to do the end behavior to see that, right? End behavior. So that's why we talked about it in chapter 2. G of x equals. On the left-hand side, g of x equals, I guess it's e to the x is the domineering term, and then on the right it's actually e to the x as well. It's just that e to the x shape being stuck on top of a parabola. And the parabola takes control in the middle of the graph, but it doesn't take control on the edges. Can you see that kind of parabola shape in the middle? And you see the e to the x shape on the edges? That's because e to the x is so powerful when either it's really large or the really large positive numbers or really large negative numbers. It tends to dominate. Just like Mr. Up on the golf course. No, not really. Okay, concavity. We should talk about concavity, shouldn't we? A function is concave up. A function is concave up if f double prime of x is bigger than 0. Function is concave down if f double prime of x is less than 0. Now what you just need to think about this as umbrella. Concave up umbrellas are really bad. They tend to hold water. Okay? Concave down umbrellas are good. Water runs off of them. So when your cat arches his back to say hi when you're scratching him, his back is concave down. Huh? So your cat is helping you with calculus. You guys just didn't know that. It's catculus. Determining the concavity of the curve. Okay, everybody draw y equals x squared. Make your math 10 and 11 teacher happy. Yeah, if you had, what is the concavity? Concave up. CC up. Justify analytically. Really, Mr. At? Take the second derivative. Y prime equals 2x. Y double prime equals 2. Is 2 bigger than 0 or less than 0? Definitely bigger than 0. Concave up. Isn't that exciting? Get your head out of the gutter, Mark. Determine the concavity of the curve 3 plus sine x on the domain 0 to 2 pi. Justify analytically. Okay, so 3. Okay, we're going to get all math 12 on it. Does the plus 3 even matter? No. There's 2 pi. There's pi. There's pi over 2. There's 3 pi over 2. Drawing sine graph. So it's concave down from 0 to pi, and it's concave up from pi to 2 pi. Is that exciting? Oh, I guess I should use round brackets. You're right, I need round brackets. Anybody think about why? Because it's changing at those points. At 0 and pi and 2 pi, the concavity is changing. I call it the itsy bitsy spider point. You'll see why when we sing the song together as a class. Do you remember the itsy bitsy spider song? Who knew that you guys were learning about concavity? Who knew? Okay, so take the second derivative. So y prime equals cos x. Y double prime equals negative sine x. So if I talk about that graph, negative sine x looks like this. So it's negative concave down, and it's positive concave up. Not the curve. I'm not talking about the curve of negative sine x being concave down and concave up. I'm talking about the y values on the graph of y equals negative sine x. Okay? I am not talking about the curve itself. I'm talking about its y values. Okay? You should have immediately gotten your eyes crossed. Like, what? That's not concave down, that's concave up. But I'm not talking about the concavity of that graph. I'm talking about its y values. Okay? Points of inflection. Let me guess. 0, pi, 2 pi are inflection points on that, the graph above. Anybody tell me what a point of inflection is? Yeah. So, where a point C, where the function changes from concave up to concave down. What do we do mathematically? What's the test we're going to do? Critical points is f prime of c equals 0. Inflection points is f double prime of c equals 0. There is no does not exist here. It's got to just equal 0. Okay, it's more restrictive. So finding the points of inflection. How to find the itsy bitsy spider point? Itsy bitsy spider climbed up the water spout. Down came the rain and washed the spider out. Come on. You guys suck. Well, dried up all the rain. I can't even remember the song. Itsy bitsy. But you need the concavity fingers. Look, concavity fingers. Concave up and then concave up and then concave down and then the other way. Look at that, eh? You're changing concavity. So when you're teaching little ones, when you have little ones, yeah, I know, but I'm doing it as a cubic function so we can talk about concavity. Who knew? Who knew? Who knew? Okay, we're going to do B because A is dumb. Find the points of inflection. So y prime equals negative 6x squared plus 12x. What's y double prime? Make that equal 0. You're 0. So what does x equal? Yeah? So how do I find the y value? Into the original function. So it's 1. Yeah? No. No. Yeah. So if we were to graph the function y equals x cubed minus blah 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 blah, it's where the curvature changes. So negative cubics look like this. So it would go through the point. It's kind of weird how you would draw it, but you would roll your wrists where the concavity changes. No, it's actually where the slope is the greatest. On that, in between two critical points, it's where the slope is the greatest. Yeah. Well, yeah. I'm just thinking about it. It is. Between two critical points is where the slope is the greatest. Wouldn't it be? I have to think about that. I'm going to have to prove it. It'll be exciting. Friday night, hanging with the boys. Okay. With the boys. Okay, so if you have f prime of... If you have a critical point... If you have a critical point... You have a critical point C, so it satisfies the equation f prime of C equals 0. Or f prime of C does not exist. So you have some critical point that satisfies that equation, or those equations. Then if at point C the answer is positive, the function is concave up there, what does C have to be? No. If you're concave up there, kids, C must be a min. And the converse, f double prime of C is less than 0. You're concave down there, which means C must be the other way. Yeah. So, Mr. F, you don't actually need to do a table to find maxes and mins. That's only for curve sketching purposes. Is if I just say find the maxes and mins on a graph, you don't actually need to build a table to do it. All you need to do is the first two derivatives. Okay, you guys do the first two derivatives. And then we're going to stop after this. What's the first derivative? 3x squared minus. Have we solved this already? What are they? I'm not caring. We just need to tell me the answers. X equals plus or minus 2. Okay, what's f double prime of x? 6x. Okay, I would like you to do f double prime of positive 2. What do you get? 12. Is 12 bigger than 0 or less than 0? Bigger than 0. We know right now 2 is a min. X equals 2 is a min. What's f double prime of negative 2? Negative 12. You know, right now, negative 2 is a max. You don't actually need to graph it unless I tell you to. You don't actually need to build a table unless I tell you to. Bum, bum, bum. And we'll stop here for now. Into the second derivative to determine the concavity. And the concavity will tell you if it's a max or a min. Okay, so we'll stop here. We'll finish this after. A level. They give you a level mark. They don't give you a percentage. Yeah. Kind of, I think. No. Probably, I don't know, maybe. 5 out of 5 is perfect. Yeah, you could. No. Yeah, fail is weird. Fail is a 0. Fail is a 0 or a 1. Yeah. Yeah. Okay, last one. A, identify where the... Okay, I can't really do this in order. I think we need to do this in well, we could do... First thing you need to do is find the derivative. And then come over here and tell me the second derivative. And the second derivative. Okay, make both of those equal 0. You're 0. Yeah, I know. Stupid. So take a 12 and an x out of this one, you're left with an x minus 2. Take a 24 out of this one, you're left with an x minus 1. So extrema occur at 0 and 2. So these are critical points, CPs. Yeah. And one is an IP. Find the intervals in which the function is increasing and decreasing. So I don't, B is very wordy. Find the intervals where the function is increasing and decreasing. What I do is just say build a table. So start at negative infinity. Go to 0. Go to 2. Go to positive infinity. So pick a number between negative infinity and 0. Negative 1. So you're going to get a negative and a negative, and a negative times a negative is a positive, increasing. And then 0 to 2, you pick positive 1. Positive, negative is a negative, decreasing. Pick a number between 2 and infinity, 3, positive and positive, increasing. Yeah? And now we'll come over and build another table. Negative infinity to 1, 1 to infinity. So 1 to infinity, negative infinity to 1 is 0. positive times a negative is a negative concave down. And then 2, positive, positive, concave up. So we answered all the questions. Have we found an extrema? Yeah. Have we built a table, tells us where a function's increasing and decreasing? Have we found the inflection point? Have we told you where it's concave up, concave down? Step 4, put pencil to page and draw a function. At 1? No, 1 is neither a minimum nor a maximum. 1 is just where it changes from concave up to concave down. It's where you roll your wrist when you're drawing. If you're an artist, you kind of know, that kind of weirdness happens, that rolling of the wrist. So, mark 0, mark 2, and mark 1. So 0. It sure would help if we found y values, wouldn't it? Did I ask you to find y values, though? No? Find where did a sketch a possible graph, just show shape, not location of point. So did I ask you to find y values? No, because my direction's in D. So we need to climb to 0, and you have to be concave down. Like that, right? Climb to 0 and be concave down, and I can't. Increasing, concave down. Climb to 0, concave down. From 0 to 2, you gotta fall, and you're gonna stay concave down part of the way. And then at the other part, you're gonna roll your wrist, and you're gonna switch from concave down to concave up. And then at 2, you're going to go horizontal for a second, and you're going to climb back out. 0, 1, and 2. So at 1 is where you switch. You're switching from concave down to concave up, but you're still decreasing. Know what I mean? Yeah, Mr. Strap, it's not so bad, or it is bad? Are we all right? Okay, flip the page. So it's just the same. It's the same stuff. So, can you draw me? You interpret what this is saying. What's the first part saying? What's this saying? Less than 0, so it's decreasing. And what's this saying? So I would like you to draw a little bit of a function at the point 2, 4 that is falling and is concave down, please. Draw a little bit of a curve. Make it decrease and concave down there. So Mr. F, if I draw something like this, that's good. Yeah? Okay, what's the one on the right tell you to do? It goes through the point 2, 4. No, because I didn't say, no, it's got to equal 0, kiddo. There's no equal 0. Critical points. So, increasing, concave up. So I'd like you to draw me a little bit of a curve that's climbing, and that will hold water if it was big enough. It'd catch water. Yeah. Just like that. Okay, what's C say? Well, through the point, 2, 4, yet again, Mr. Up. What happened? Doing this to me. Okay, through 4. Point. Horizontal. What's this bit saying? Concave down. So you're going to go through the point 2, 4 again, but I want you to be horizontal there and concave down there. What's that point? A max. Okay, what's D? It is a critical point. You're going horizontal for a second, but to the left of that point, you're concave down, and to the right of that point, you're concave up. So go horizontal for a split second, but to the left of it, you're concave down, and to the right of it, you're concave up. Is that a max or a min? No, it's just a flat spot on the curve. It's like St. Paul when you're going up First Ave. It's a flat spot on the climb, right? Yeah. Okay, next part. If f is an even function, we'll talk about that in a second. So, when I want you to plot these points, I want you to plot 0, 2, 1, 0, 2, negative 1, 0, 3. You can plot those. Zero, 2, 1, 0, 2, negative 1, 3, 0. Mr. Why don't you spread it out a little bit more? It doesn't need to be so tiny. 1, 2, 0, 1, 0, 2, negative 1, and 3, 0. Okay. So we've got the points plotted. Check. F prime is undefined at those points. So what does that mean? Or, yes, okay, these are automatically all critical points. These ones are horizontal. So at 1 and 3, we need little tiny horizontal bits. What do we know about undefined? F prime of x is undefined. Or cusp or a corner or vertical tangent. So we don't know what these are quite yet. Cusp, question mark. Corner, question mark. Vertical tangent, question mark. Okay, so we'll leave that for a second. Between 0 and 1, this is how we can read this. Between 0 and 1, we have positive y values. Duh. Look at the graph. Between 0 and 1, f prime is negative. That means it's decreasing. Between 0 and 1, f double prime is positive. Concave up. So I would like you to join the dots, to join the points 0, x equals 0 and x equals 1 with a little bit of a curve that falls and is concave up, please. How's that going to look? Everybody draw it in the air with your fingers. Yeah, most of you are doing it, so good. I'll assume that the rest of you know what's going on. So Mr. App, it's got to look like that. Okay, between 1 and 2, the y values are negative. It's falling, and it's concave down. So how's that going to look between 1 and 2? Thanks. Between 2 and 3, it's negative y values climbing concave down. Ah, you've got a cusp there, Mr. App. So you've drawn half of the graph. What does even mean? We talk about even. Symmetrical about the y-axis. Yeah. Make this function symmetrical about the y-axis. Take the graph and reflect it. Ah, those were cusps, you silly rabbit. But I didn't tell you that they were. What? What do we do by what? Because it said even. Even means symmetrical about the y-axis. Yeah. That wasn't bad, was it? See how this is kind of interpretive? A function is continuous on its domain 2 to 4. Okay, so it's just curve sketching here. So a function is continuous. F of 2, negative 2 equals 5, and f of 4 equals 1. Okay, well, I don't know. Maybe you guys should tell me some things we could do right away. Plot the points. Open circles or closed circles at those points? Closed. Oops. I'm an idiot. How's that so far? Got the 2 points. Okay, what else? I'm going to zoom out a little bit. Do we have a graph at the bottom? I'm an idiot. Okay. Dummy. One, two, 3, 4, 5. 1, 2, 3, 4, 1. Okay, now what? What does this mean? Climbs and is concave up. Did I tell you how far to climb? So climb. Climb until you get to 0. And then stop climbing. So could I do this if I was like a grade 8 boy? Because we do these kinds of things. Yeah, we could. Isn't it exciting? Mr. F saying to draw all over your page. Yeah, okay, so we're going to climb to 0. Okay, at x equals 0 does not exist, so that's indicating right away to us that it's either a corner point, a cusp, some sort of vertical tangent, something like that. We don't know yet. Between 0 and 2, what are we doing? Falling and still concave up. Oh, so at 0 we have a cusp. Now, did I say how far to fall? No, but you got to be careful because we're falling and then we're falling some more. You don't want to fall past 1 because you can't climb into it. Right? So fall and then fall some more. And at 2, go horizontal for a split second. Fall. And then fall some more. But watch how you fall. You're concave up and then you're concave down. So what do we know about, what do we know? Find where all absolute extrema occur. A, where is the absolute max? Yeah. Where's the absolute min? Find out where all points of inflection occur. Mr. Epp, there's only one point of inflection. IP at x equals 2. So I kind of did it backwards, hey? Kind of like to draw the curve first. Is that bad? Finding the point. We've already done this. Look in your notes. Do you want to do it again? Is it fun? Would you like to do it again? We've already done it once. No? Okay, flip the page. So, using the graph of f. Use the graph of the function f to estimate where f prime is 0. Okay. So, what we're looking for here is, for A, we're going to use colors because this will be fun. We want to know where f prime and f double prime are positive and negative. That's good. So where is the function's derivative positive? From about here and left, it's positive. We're going to get colors all over the place. It's going to be fun. So f prime of x is bigger than 0 when x is in the interval negative infinity to negative 1. Where else is it positive? Left, right of 1. And the interval 1 to infinity. Where is it negative? What? From negative 1 to 1. Where is it equal 0? 1 and negative 1. Okay, where is the second derivative? Negative. Where is it concave down? Left of 0. Where is it concave up? Yeah, 0 to positive infinity. Where's the inflection point? So there's that graph. Here's a stupid question. Are the properties of the graph any right any different? If I remember correctly, if I don't slide over, does it really matter that it's been moved? I just gotta make sure I'm not an idiot here. Does it really matter that it's been moved up? No. The properties are exactly the same. Do you see that? I guess that's a question that you can't really answer, is it? Oh wait, neither's that one. The properties are exactly the same. The concavity and the increasing and decreasing are all the same. Okay. Yeah, but it doesn't matter. Oh, it's at 2. Oh yeah, sorry. Yeah, you're right. So we could do it, I guess, but I mean those are the points you're looking at. You're going to talk about, you're right, I'm dumb. So it's increasing, but left of, I don't know, -1, and it's increasing to the right of +2, and it's decreasing between -1 and +2. Yeah, like it's easy to look at an original function and tell me what's going on. But when you have to look at the derivative graph, it's actually a little bit more complicated. Well, actually it isn't, but I'm going to put a little chart at the bottom of your page that will help. Y equals f of x, y equals f prime of x, y equals, oh wait, how do I want to do this? Yeah, no, that's how I want to do it. Okay, tell me all the properties that the graph of y equals f of x has. They have x and y intercepts. They have maximums and minimums. They have positive slope-ish. They're increasing and decreasing. That's a better way of saying it. And they're concave up and concave down. The graph of y equals f of x is a very specific graph. When you can graph y equals f of x, you can say everything about everything, because that's the original function. But as you look at other graphs, as you look at the derivative graph, information is lost. And as you look at the second derivative graph, even more information is lost. So when you're starting with the second derivative graph and I ask you about the original function, all you can tell me is about its concavity. You can't tell me anything else unless I give you more information, which you need to worry about at a later date in chapter 7. Then anyways. Yeah, notice how far away it is before we start talking about going backwards. So, as we go to the derivative graph, this information is lost. You can't, if I graph y equals f prime of x, you can't tell me about the x and y intercepts of the original graph. You can't. Unless I give you, there's always an unless, but for right now there's no unless. You can't do it. Maximums and minimums become x and y intercepts. Sorry, x intercepts. They're the bumps. Did you notice? Like if I was to draw the derivative graph, I'm going to go up and I'm going to scribble for a second. I'm just going to draw the derivative graph of this. the derivative graph for this function would look like this. Positive slope, negative slope, positive slope. Right? X and Y, the bumps, the maximums and minimums become x-intercepts. Okay. Increasing and decreasing become positive y coordinates and negative y coordinates. Concave up, concave down become increasing and decreasing. You can think about it as positive slope and negative slope if you want. You can think about it as climbing and falling if you want. Now here's the part where it gets really interesting is, now we take the second derivative. Even more information is lost. All you can talk about is positive and negative y coordinates, sorry. Everything is lost. There's no characteristics around that you can talk about on the original function. It just doesn't do anything for you. What's the only thing I didn't put on this table? I was stupid and didn't put it there. No, I got that. IPs. IPs become maxes and mins, become x-intercepts. So if I give you a second derivative graph, all you can do is go backwards and talk about where the derivative is increasing and decreasing, or you can go a little bit farther back and talk about where the function is concave up and concave down, and that's it. Okay? Okay? I love this table. Nobody ever made this for me when I was in high school or university. I didn't get to get calculus in high school, but in university. This is something that I've come up with over the years. So, this is the derivative graph. I'm going to talk about y equals f of x on the derivative graph. I see positive y prime values. Would you agree to that? All those circled areas, positive y prime values. Yes? So that means positive slope. It's climbing. You can say, I don't want to even say positive slope. I want to say climbing. Climbing. It's climbing when it's above that axis. What's it doing down here? Falling. What about these 3 points? It's neither climbing nor falling, Mr. App. They are horizontal. These are critical points. Exclamation point. Now I'm going to switch colors. So I talked about, what did I talk about there? I talked about all the y prime coordinates. The y prime coordinates tell me about climbing, falling, and critical points. Okay. Now I'm going to look at the shape of the function. Tell me about the slope here. Concave up. Tell me about the slope here. Concave down. Tell me about the slope here. Concave up. And then I get really funky and I circle these 3 points. 2 points. Those two. Those are inflection points. Itsy bitsy spider points. Climbing, falling, CPs. CC up, CC down, CC up, IP, IP. Okay, so we're going to look at the one on the right and do the same thing. Tell me where it's climbing. Climbing everywhere except for, you know what I mean? Like climbing. Climbing. Where's it falling? Yeah. Falling. Where's the critical points? Come on. -2 and 2. Critical points. Okay, so all that's done. We talked about our y prime values. Now we're going to talk about the slopes. Positive slope. Concave up. Negative slope. Concave down. Positive slope. And then get the other circle out and go, cool! These 2 points are IPs. So you've got a point on this graph that's a CP and an IP. Isn't that awesome? It's doing 2 things at once. Who cares, right? Well, I don't know. It's climbing there, and then it's switching from concave down to concave up. It's an itsy bitsy spider point, kind of. It's doing this. It's like, kind of like that. Anyways. Okay, that's enough. Yay. Okay, so, got half an hour. Not a half an hour, I guess, it's less than that. It's Wednesday. Working on 4.1, 4.2, and 4.3. You're chatting with me if you're stuck on something. Yes? Yes. Okay.